Hey guys, welcome back. This is how you draw a free body diagram for an object that's resting on an incline. And the reason we want to do this is to determine certain parts of its motion, like how it's accelerating down the incline or how far it goes, etc. We can also use this to identify components of an object's weight on the incline. The first thing that we're going to do is draw the incline. So we're going to note some geometry. If we take this XY axis and we rotate it through some angle, you're going to see that a lot of the angles are the same. This will be the ramp. So notice I've taken my axes and I have rotated them through some angle of theta. And this is going to be the angle of the incline here. And I'm going to draw a new y-axis along this line. So this angle here is also angle theta. So if this were 35 degrees, this would be 35 degrees. This is the new y-axis. This is the new x-axis. All right, next I'm going to transfer this over, and I like to draw the ramp when I'm drawing a free body diagram. You don't have to for the final product, but this is a step in showing you how it's done. I need a perpendicular axis here. Again, this is y, and this is x. And here's my object. So I'm going to go back to this diagram, and I'm going to use this line here to draw my first force vector. That is going to be the force of gravity, or the weight of the object. And this vector is always drawn downward towards Earth, since Earth is applying that force. We're going to label that FG for force of gravity, or the weight of the object. Again, we have two angles here that are the same. Note that these angles are also the same here, here, and here. Now, if we take this force of gravity vector over to the y-axis and make a right angle, we can identify two components of the weight, and these will be important. I'm just going to lightly sketch them. The one from the origin downward to this right angle is going to be the force of gravity in the y direction. In other words, this is the component of the object's weight that is perpendicular to the surface. The other component of the weight is the component that causes the object to slide down the surface, and this is the force of gravity in the x direction, FGX. So this is the force that is causing the object to slide down, okay, FGX. Now again, this is just a component of the weight, so it's not an actual vector that we're going to draw in our diagram. But there is some similarity here. So the force of gravity in the y direction, this component that's perpendicular to the surface, this is equal to and opposite to the normal force that is applied by the surface. And the normal force is always applied perpendicular to the surface. So this is Fn, our second force vector for our free body diagram. It's equal and opposite to the perpendicular component of the weight. This is different from what we've previously done, where if the object is on a horizontal surface, the force of gravity, or the weight, is always equal to the normal force, as long as there is no net force on the object. So here, the normal force is going to be less than the weight of the object. As we increase this angle, that normal force changes, and it causes the object to accelerate downward faster. Okay, there's one more vector. If the object is on a surface that has friction and the object is sliding downward, then the force of friction vector is drawn up the ramp, FF. Now, again, I said there were some similarities. So this force of gravity in x direction pulling this object down the ramp is equal to and opposite to the force of friction. So this should be the same size as this vector, force of friction. If we look at static friction, then there's a range of static friction where if we increase the slope of this ramp, eventually we increase it to a critical angle where the object will start to slide down and overcome that force of static friction. So whatever the force of gravity in the x direction is for that lower angle, as it increases and changes, the force of static friction also increases with it. So as this vector changes size, this vector changes size. Eventually, the object will slide down when that critical angle is reached, and we can analyze the force of kinetic friction. So as it's in motion down the ramp, whatever this force of gravity vector is, based on that angle, is still going to equal this force of friction opposing it. Last thing to consider is if the object is being pulled down a ramp or up a ramp. We will have an additional vector here, and I'm just going to lightly sketch this, for the force applied, FA. And that would be adding to this force of gravity component here. If the object were in the opposite direction, you might have like a rope attached here. There would be force of tension. And then the force of friction would be in the opposite direction if you're trying to pull something up the ramp. So keep that in mind. We're going to take what we've drawn here and finish our free body diagram. Here is the particle to represent the object. We have a weight vector downward. And notice the angle here for the normal. And our third vector is for the force of friction. Again, that is equal and opposite to the force of gravity in the x. And if the object is not experiencing a frictional force, we can eliminate that. So if the object were sliding down an icy surface where it's nearly frictionless, the only two factors or forces acting on it are the normal force and the weight. All right, so now we have two free body diagrams, one where friction is acting on the object and one where it is not.